the charger?
In case.
In case, yes. Yeah. That's a good idea. I'm dragging him into transportation seminars. And he's dragging me into water seminars. I'm also curious, what is this? Infrared to count students? He was facing that way. What is the time? It's 3:30 already? It's about 3:30. Okay. Good afternoon, everyone. Thank you so much for making the time on this Friday afternoon. And we have the pleasure here of hosting Professor Ma. But I'll let Zishun introduce him formally. Before that, I wanted to say a couple of words about the Future City Initiative and the Future City Seminar Series. We have established the Future City Initiative in 2018 under the leadership of Dr. Ati, and now we are continuing under the leadership of Dr. Mackey. And under that initiative, which includes the educational component, research component, Future City Seminar Series was one of the key components where we invite distinguished professionals in the transportation and smart city area to come and visit the campus, interact with the faculty members, and discuss their research work. So with those words, I'll let Professor Zishun introduce Professor Ma.
Yeah, thank you, Shora, for introduction. So yeah, Dr. Jiaqi Ma was my postdoc advisor, so it's my pleasure to invite him here today. So Dr. Jiaqi Ma is the director of the Federal Highway UCLA Center of Excellence on New Mobility and Automatic Vehicle. Is a professor at UCLA Samueli School of Engineering, Department of Civil and Environmental Engineering, Department of Computer Science, and the director of UCLA Mobility Lab. His primary research interests include autonomous driving, physical AI, mobile robotics, multimodal sensing, cooperative perception and decision making, mobility digital twins, spatial data mining, reasoning, and simulation. Dr. Ma served as the editor-in-chief of the IEEE Open Journal of Intelligent Transportation System and senior editor of IEEE Transaction on Intelligent Transportation System. He's also the chair of Transportation Research Board, TRB, Standing Committee on Connected and Automated Vehicle System, and a member of Board of Governor of the IEEE Intelligent Transportation System Society. So welcome, Dr. Ma, for this excellent talk.
Thank you. Thank you, Shikran. Yeah, thanks so much for the invitation. I really glad to be here in Orlando again. I told Mr. Chair that I'm a frequent visitor to Orlando because of other activities that is happening here, and because I have a 6-year-old daughter, so we have to be here. You know.
But you live in LA. Yeah. You have the same stuff.
Yeah, but we want to. Yeah, the Disneyland is enough. You know, so Disney World is we want to experience Disney World anyway. So my topic today is the multi-agent mobility systems. This is the topic that to the heart of myself and my team has been working in different aspects of multi-agent mobility systems. I will tell you how we define it. Different people may define it different ways. And also automation and connectivity, how that will transform transportation and transform this multi-agent mobility systems is our big focus in our lab. So I'll get started. So just quickly about our lab. we do this couple of things. One, the first thing from the left and all the way to the right, right? So we first develop digital twins, simulation or other types of twinning representation for the cities, for the systems. And then we go up there. This is where we kind of innovate, where our theoretical contributions are. We talk about multimodal autonomy, where we're looking at this new systems, sensing, decision making, predictions, and so on, right? How they will impact the next generation mobility and transportation systems. So this is where a lot of papers we write, and then we kind of innovate on the methodology. Then we have a living lab we call Digital Westwood. We have intersections equipped with different sensors, and also build again the digital twins for the Westwood area. So where we do simulation for sure, but we also have real world tests using our automated vehicles and roadside sensors. We have another area of research, actually it's the area that we worked a lot with Dr. Xu is the urban AI aspects, how we model the system, modeled every individual component of the system. And then last but not least is the edge AI component, because a lot of the where the smart city applications will be deployed on the edge, either on the roadside infrastructure or on maybe these mobile robots, vehicles, and so on. These are in total called edge. In most cases, there will be resource constraints in computing, and we want to make sure that these things works even under the resource constraints environment. So multi-agent mobility systems, we worked on, this is kind of how we define it at different scales. First of all, these little robots in logistics centers, distribution centers, right? Nowadays, you see less people, but more these mobile robots coordinating each other, working with each other, and completing these logistics tasks. Then at sidewalks or also intersections, you have different types of pedestrians, and even mobile robots in the future, right? Like for example, Tesla's Optimus. But eventually, they will interact with each other. In this case, we're working with another professor on this autonomous wheelchair, and in particular, we're interested in how they navigate themselves on the sidewalks and how navigate themselves in the intersections. And then this is where I spend a lot of time on, is where at an intersection, right, this is where for transportation engineers, this is where all the conflicts happens, all the crashes happens, and how we better sense this environment and enable agents or autonomous agents in this environment to make bad decisions, and also protect those non-connected, non-automated agents in the systems, right? In this diagram, you see there the little bounding boxes there. Those are pedestrians that we have to identify them and protect them. Last but not least is the work that I will mention quickly today, but Professor Xu has been, we're working together on this, is more at a system level, how we simulate each of the individual agents traverse across the network. That's a much higher dimension problem because in this case, it's not with these local goals navigating through the intersection safely, right? To some extent, that's an easier question because that's a goal is so simple, so well defined. But in the urban mobility systems, let's say, for example, you want to understand, LA 28, like Olympic Games. What's going to happen, to LA during Olympic Games? That's almost a question impossible to answer because you think about it, every mobility patterns will be changed. So how to model that is actually non-trivial. But I will mention a little bit, but Professor Xu and I work together on this. He knows much more details. So let's zoom in to what we talk about at the vehicle level, at the intersection level. Obviously, autonomous driving or automated driving, I'll use them interchangeably in this case, but automation has different levels. I'll briefly mention them in a minute. But autonomous driving obviously is going to transform our mobilities, not only locally when vehicles interact with each other, safer maybe, But more importantly, they're going to also change the entire mobility systems, right, at the transportation mobility system level. And again, these robots here, they are going to be very critical. I deeply believe they are going to be very critical parts of mobility system in the future. It's not too late to start including them to mobility systems, because, for example, this guy, he's occupying your sidewalk. One of these guys is fine, but then how about 10 of them in a short segment of sidewalk, which is originally designed, reserved for humans to move around? And especially people with disabilities, we design the sidewalk sufficiently for those special needs. But if these guys are operating on your sidewalk, what's going to happen, right? So I think that's also a very critical question for us to understand. At intersection level, or from infrastructure level, so one important things we have been working on is called intersection safety systems. This is where you have connectivity at the intersection, where you're sending, distributing different information, of different agents. For example, some of these vehicles might be equipped with communication devices, and they will send information to other agents. If there's or for example, broadcasting basic safety messages, right? This is kind of standard connected vehicle protocol. Or they see, let's say if infrastructure see a very safety critical scenario or potential crashes, infrastructure may send out warning messages through either personal devices or roadside infrastructure warning signs, maybe. But also importantly, things that sensing is a big part of it, right? Sensing will be installed not only on automated vehicles, but also on the infrastructure. And what different types of sensors, LiDAR, radar, camera, different types of sensors. They have different use cases. What are the good combination of them? And also, there's a non-connected, non-automated users in this environment. So vulnerable road users, for example, right? There's a couple of folks here. They're crossing the intersection. For example, this mom is pushing the strollers through that crosswalk, but then this particular red car is going to turning right. This is actually a very dangerous scenario in this case. So scenarios like this should be avoided, or at least this red car should never move under this scenario. So we want to talk about this, right? So this is at the infrastructure side. Now vehicle side, infrastructure side, they're all connected if they might be connected or not, right? Then there's sensors on the roadside and both on the infrastructure side. A lot of work has been done in this area over the years. You can have intersection safety system by itself, but you can also have the vehicles, right? They are also operating in the environment. But the problem of these systems is that they definitely work very well, especially autonomous vehicles developers. They're like, okay, I'm gonna just making sure that my vehicle is be able to operate by myself completely safely. That's how ADS developers, we call them ADS developers like Waymo, are developing these systems. However, we're talking about a different type of systems here called a multi-agent system. It's where different agents may know the intention of each other, or they know some data, right, of each other. For example, these several vehicles in the traffic intersection, if they're connected, they might share data, some sort of data. I will talk a little more about it, with each other. And this sharing may help facilitate their joint decision making or help improve safety. So that's what we are talking about. And absolutely, all this data can be collected by infrastructure. If they have a better seeing of the environment, right, usually less occlusion and expanded view, then they can make much better decisions, from an infrastructure management control perspective. SAE, Society of Automotive Engineers, actually defines this already, right, pretty well from a conceptual level. The different columns here is different levels of automation. That's autonomous vehicles. That's automated vehicles, different levels. All the Waymo we are talking about here is actually level 4. And there are different classes of information sharing, status sharing, intent sharing. So the status sharing is basically sending out their own messages all the time, broadcasting their status. But intent sharing Also, I forgot to mention that status sharing also include what I see. Even though this is just 3 words, right? It's very powerful. What I see means that my sensor, I see this my surrounding, that becomes a message. And I share this message with all others in the environment. That basically will significantly enhance any agent's environmental awareness in that, for example, intersection. And there's some higher levels of different types: intent sharing, agreement seeking, and so on. These are more high level, like coordination between different vehicles. It's harder to achieve these days because fully connected automated vehicles really doesn't exist in the short run. But at least the information sharing part is the part that we have been closely working on. We published a paper called OPV2V. This is a data set, a pipeline paper where we define how many different ways can different agents share data. We define early fusion where they share information, the raw data, and then we define late fusion. That's basically each agent will complete the detection tasks, and there's going to be object list, and then you share with each other. And then there's an intermediate fusion. This is where you kind of go back a little bit, because especially when the vehicles from the same companies, right? They share the same neural network model. They can actually share some feature space of the neural network, basic sharing features. And then if you compare with the object list, you're reserving more information by sharing feature spaces, and then you fuse that. That will give you, in many cases, better results of fusion. So this kind of originally defined the 3 different ways of fusion. Obviously, the early fusion is our baseline, right? Nobody will share raw LiDAR data because that's too huge. And late fusion is intermediate fusion is what we have been exploring, kind of in parallel streams. There's a lot of engineering challenges in these fusion problems. It's not just like, for example, 2 fixed cameras, right, with fusion their data. Think about vehicles keeps moving, and vehicles get its own localization error. Sensor have different heterogeneity from different vehicles, right? Tesla is camera-based, and then Waymo's obviously has multiple sensors, but if there's another vehicle may have a very heavy reliance on LiDAR sensors. So how to fuse this data together is a very non-trivial question. So there's a lot of engineering issues. And again, there are different type of agents, right? A vehicle is one type of it. And there's infrastructure sensors. Infrastructure sensors are usually mounted pretty high. They usually have a good view, but the infrastructure are subject to other problems as well. To do this, right, I just want to mention this quickly. We developed a tool called OpenCDA. It's built on Carla, and also integration with Sumo and many other modules. We are still developing this community and moving this to a bigger community called DriveX community, where we share data, share simulators, share data sets, and create work challenges. Just be able to, looking at multi-agent research. Okay, along that line, we developed a couple of models. As I said, in this case, this work is probably where we did 2 or 3 years ago, where we're looking at how our question is that how to define a common framework where vehicles and infrastructure can share data together. And because in the past, before this work, most of the work is only vehicles sharing data with vehicles. To me, infrastructure plays a special role in my heart. So I want to make sure the infrastructure is also part of the story. And it's obviously we have to treat it separately, because the way infrastructure contributing to data is very different from the way a vehicle will contribute to data. As I said, it's different enough that you cannot really using the same model, right? You can just throw into the same backbone and treat them all together the same and let them fuse together. So we have to treat them separately. So what we did is there's a kind of graph, heterogeneous graph in this case. This is a good example where we have an infrastructure node and a vehicle node. And basically we feed the model with different scenarios of different data, and then let the vehicle know under what scenarios, when the infrastructure is installed at different locations, different angles, and how much weight infrastructure should play in this cooperative perception task. Now again, there's other treatments like how we consider communication delay. There are places where we consider different resolutions of data, different sensors. This also included localization errors, right? So, for example, if we using very detailed grid feature space, then the localization may throw things off. Localization error may throw things off. But if we kind of using this multi-resolution grid scale that helped us actually, eventually improve the robustness of the system. This is a diagram I always show. This is a visualization of attention, which is basically weights, right, in the neural network. And this is the scenario. And where you can see here is attention weight B is attention weight ego vehicle paid to ego, right? The brighter, meaning the weight is higher when I fuse all this data from vehicles and infrastructure. The ego vehicle, in this case, only paid attention to itself, to its own data in the immediate surrounding area. Now, this is ego vehicle paid to AV2, which is at that place. Only in that place at a surrounding ego vehicle, AV2. And then attention weights ego paid to infrastructure. In this particular example, now I have to admit this is a pretty extreme example where infrastructure installed at that very nice location where there's no occlusion, there's a very good view of everything at the intersection. So the infrastructure the training model basically says, okay, you have to use my infrastructure data in all these different areas where it's bright here. So this is actually encouraging results. Tell us that infrastructure data can, if managed well, play a very important role in this connected systems, helping human-driven vehicles, any road users, definitely include automated vehicles, to better sensing the surrounding system. So this is kind of one of the results that I was very glad to see. And obviously we did some sensitivity analysis, robust assessment when there's heading error, localization error, time delay when exchanging messages. If you, this is kind of the components that we explicitly included in that model I just mentioned. Our model becomes pretty robust in front of these different errors. We look at another paper, which when we realize, we acknowledge, right, there's different sensor types. LiDAR and camera is probably one of the two most famous, widely used sensor types on these automated vehicles. So if you really want to develop a system that can fuse both vehicle infrastructure, you have to fully consider, right? For example, Tesla's here, Waymo's there. Then you have an infrastructure system using whatever camera or multi-sensor approach. So we kind of improve that work, building a kind of dynamic heterogeneous graph. It's a very similar concept, but it's a different paper we wrote to fully acknowledge the attributes of different sensors. In this case, for example, camera and the LiDAR, right? So we actually using this graph-based approach, but we kind of separate them. Each plane is actually a node, right? An agent, their contribution. So we had to fuse them in different ways because again, there are different. We explicitly, basically, right, acknowledge that the contribution from LiDAR or camera is different. And then we let the data, we collect it. In this case, actually still simulation data, but later we apply the same model to real world data to understand, to learn how important they are. A good important findings is that we realized that we have been using this detection accuracy as our performance metric. What we found is that as long as your LiDAR, it kind of boosted the detection accuracy significantly. It kind of discredited the existence of camera. But the result is good, right? We still see, if we fuse them, we explicitly consider them, we still see this fusion algorithm still good. But we realized that after this study, detection accuracy might not be the right performance metric for us to evaluate perception systems like this, right? Because again, you need much more things than this to be able to manage your intersection better or improve your safety. Another work we did along this area is pre-training, because a lot of this work we did consumes a lot of data. Every time we have to retrain everything. So there's a pre-training method. Basically, it's a reconstruction approach. Eventually, what this problem is that you have LiDAR here. You have your point clouds on the same object. And depending on the relative position, the distribution of this point cloud distribution will be different. Now, this is similar to a single LiDAR, but if you have two LiDARs or multiple LiDARs, the distribution, the number of the ways or scenarios of the distribution can actually increase. So it's actually a more difficult problem. You have more scenarios, you need more data to be able to train a better model. So in this case, data efficiency becomes a problem. So we were thinking about an approach that, how can we pre-train a model, right? This is kind of aligned with a lot of the language models concept, the GPT model. They are pre-trained models. How we can pre-train a detection model, and then this model will be fine and have this risk using this reconstruction capabilities to retrain it, and then fine-tune those type of models at each individual intersections. That's kind of the question we discussed this morning. Is that in Florida DOT want to deploy this type of system, infrastructure detection systems at 500 intersections, each intersection will be unique, actually. So what is the way to be able to scalably deploy those intersections? This is the one approach we did. Pre-train first, and then we develop also corresponding fine-tuning methods, so that we realized that there's a 50% of data needs actually reduction, and the performance is still as comparable as before, but the actual data needs is less than 50%. After that, we decided that playing with simulation data, because we got more and more criticism from using simulation data only, so we had to create some data sets ourselves. This is one of the efforts that we deployed at our intersection. So we kind of over-equipped this intersection with a camera. We have 4 cameras pointing each of the approach. We have 2 LiDARs on each of the corner, and we have 2 radar systems. In fact, ideally you need 4 radars, I think, but we have 2 radar systems. And obviously, to do the experiment, we have 2 vehicles in this experiment as well. So we over-equipped this intersection just to be able to collect the data for whatever purposes we just talked about. And also we defined this problem of a vehicle-centric perception problem, infrastructure-centric problem, and then obviously vehicle-to-vehicle communication, and also infrastructure communication. So we kind of define different types of problems, and also the data size is bigger. It took us almost a year and a half from collection all the way to be able to labeling all the data and release it to the community. So this paper, again, we define all the different, especially infrastructure-centric, right? There wasn't actually people working on this problem, so we define the infrastructure-centric, just again, help, right? People to experiment, understand it. What is the role of infrastructure perception? We did also, at the same time, when we collect data, we actually deployed the airguns I just mentioned on our vehicle. So this is actually an experiment, a video. I directly took this video from our vehicle. If you can see here, this is the real-time detection results. I didn't even using tracking or any post-processing. So if you see here that, so this Eagle vehicle is here, but this Eagle vehicle is still able to see some of the agents here, right? It's just because that the infrastructure, which didn't visualize in this case, the infrastructure, this is only visualizing from the vehicle a single vehicle perspective, but we do have infrastructure data from the corner, two corners. In this case, I think we only work on two corners, I think. If you see all those data, vehicles from nowhere, that's basically infrastructure telling this vehicle, hey, there's something on this. But the one key thing of this experiment is different is that it's resource constraint. It's we plan it on vehicle, and a lot of fancy algorithms we developed immediately fail, right? In this case, because the inference time is too long. So we have to actually compress our models a lot to be able to deploy it on this vehicle. In fact, this vehicle has a nice GPU. Even that, we don't. Those traditional algorithm doesn't work. So we have to compress our models. So that's one interesting lesson learned. And we did in this paper. We did compare, how much you compress will kind of saving, reducing the latency, and then different types of models and related to latency as well. Because again, this is a big thing for us, right? Our requirements at least 110 hertz, right? 100 milliseconds. Every delay has to be below 100 milliseconds. So that's kind of our thinking. And unlike our previous papers in simulation, we kind of said, okay, intermediate fusion, or it's very nice because it keeps more information. Then in the real world, everything kind of changed. We look at different algorithms, different late fusion, intermediate fusion. We find different scenarios, right, under different infrastructure-centric or vehicle-centric situations. They perform very much differently. For example, you can see here, in some cases, the early fusion, the intermediate fusion doesn't even perform well as late fusion. Very simple late fusion, basically, two bounding boxes fusing together. That's obviously one of the main reasons because of the latency. Even though we were able to make it, run below 100 milliseconds, but still, there's other delay of the system. There's other parts of the system that causing delay, so the performance wasn't very nice. But anyway, at least this provided a benchmark, a real online. We kind of tell the community who works in this area, which was this was a hot topic 2 years ago. I think a lot of those conferences, a lot of the papers on this. But we kind of started with the intermediate fusion work, and then we kind of say it's good. But then I told my team that it's time for us to do the experiment and tell everybody that don't fully trust the intermediate fusion. Right? By definition, it's good, but under a lot of these constraints, it's not good. And also another reason interesting thing we discovered from here is that the feature fusion algorithm failed immediately at one of our approaches, because all this LiDAR feature extraction algorithm assumed a flux surface. One of our other three approaches works totally fine. But one of the approaches we had at the intersection has a non-trivial slope. So there's nothing being detected in this place. I think our team debugged for like 2 days. Didn't know what happened. Then because of that assumption. And a lot of people just download the algorithm, including our team, I guess, the base LiDAR extraction, feature extraction algorithm, and applied it. But we never realized that was the main reason causing that. So there's much more things to tweak, that's the idea, in this kind of intermediate, fancier fusion approaches. For the regular late fusion, you just fusing bounding box. You lose more information, but to some extent, right? Because it's already there. That's more robust approaches. So after all this perception work, obviously we're not satisfied with that, because eventually perception or detection perception is just one part of the pipeline. We want to inform downstream. Now, one of the important downstream tasks is prediction. And prediction can help you directly inform road safety systems, vehicle trajectory as well, right? If it's an automated vehicle and so on. Also, pedestrian warning messages, right? I have to be able to predict, okay, there's a potential conflict. And then if that happens, then I have to issue warning. So we want to see that, okay, how that, so far if you can see this work, is all frame by frame. So we are on each frames and fusing all this data together. But obviously that's not sufficient, We did another work basically adding the time dimensions to it, right? And that with the time dimension, we're able to predict this information better. So this is the, I will not do all the details, but the idea is that how we at each, but we also need to ensure the efficiency of this communication. So you cannot communicate, every time step, you communicate like 10 slices of information, right, without this. One slice of information is already too much at each time step. So there's no way you'll be able to communicate 10 slice step at every 10 hertz level. So what we did, we further compress, right? At each time step, we compress. In this case, I think we probably, in our case study, we're probably using 5 slices, each 0.5 second in the past 5 time slices. We compress them temporally, and then we further compress them, through the traditional compression method, and then share it with other vehicles and infrastructure. So there's a lot of compression happens here, but what we want to see is that how much of the information, the temporal information, after temporal compression, how much it has been actually maintained. This is the algorithm. The one down there is we have basically using a temporal attention block to compress temporally first, and then spatial attention block to fusing spatially. That's a multi-agent fusion between each other. This is for each agent we compress time level. So we think that temporal information is critical, but we don't know how can we actually compress like that. Again, for this work, we expanded the data collection. That intersection in the middle is actually where you see the small intersection our deployment are. But obviously, this is more trajectory vehicle prediction, so we are not necessarily limited to that one intersection with infrastructure. So we actually expanded more data collection. This is more urban. This is more urban arterial. This is higher speeds. This is slightly lower speeds. So we kind of increase the diversity of the data a little bit. But again, we developed this data set to be able to test to train our model and test our assumption, how to compress the temporal data, and then works. So the result is here, right? So if you can see, V2X GMP is our result. So the prediction, the red is the ground truths, the green is our predicted results. Compare with other methods, obviously we see that the temporal, this is even late fusion and also our traditional feature-based fusion. So obviously we were able to capture the temporal information very well. So if you look at this Appalachian study, so this is where, for example, let's see this. I know there's a lot of data, but if you can just see this, this is the temporal information, right? Adding this with and without this temporal information actually resulting a significant increase from 43 to 5, for the AP from 43 to 57. So that's a huge jump in performance, right? If you're looking at others, for example, from this to this, it's about 10 points at spatial fusion. Here adding a map, that's so limited. But anyway, the temporal value, the temporal information added to your system is very valuable, as proven this, right? And then again, as we did before, we kind of did a sensitivity analysis to show that it works in every other cases. So here is the thing, right? So we talk about multi-agent fusion, but so far it's a very traditional pipeline, and we don't know if this actually kind of works in the real world, right? It's traditional pipeline that looks at prediction, detection, tracking, prediction. But in the real world, there's a super complicated like this, scenarios like this. And this is actually at our small intersection. We picked that intersection for a reason. But this is actually added a complexity because there was a work zone in that period. And then there's a pedestrian crossing, and there's a bicycle lane, there's a special signs. So in the real world, these automated vehicles will need to navigate through complex environment like this. Even the humans are challenging challenging for humans to understand. So we said that there might need some higher level of intelligence needed, and the time 3 years ago, maybe 4 years ago, when we discussed this problem, this is when we had a project to looking at how automated vehicles will comply with the traffic rules and the regulations. Because that's a very unique problem in the US. From places to places, jurisdictions to jurisdictions, the traffic rules and regulations can vary. It's not totally different from state to state, for sure, right? For example, I think state of Oregon doesn't allow your vehicle to cross the stop bar during the yellow light. I think so. So things like that, and a lot of places allow right turn on red. That's a major thing, right? A lot of places doesn't allow that. So how even vehicles, I cannot, let's say, all the problems, all the work we talked about so far is detecting that pedestrian. Detect that pedestrian reliably, okay. Assume that's done, but now what? If this pedestrian is here, can my automated vehicles go across? Even though it's a red light now, but if it's a green, can I go across this stop bar, right? That's the kind of question we try to address in this problem. And then we think about, at that time, it's funny, when we started that project, there was no ChatGPT, there's no large models. And during the middle of the project, there's a GPT came out. It was so nice, right? It's just such a nice thing. And I tell, before that, we were like looking at traffic rules. We kind of cut them into different small pieces the machine can understand. But when GPT came out, I was like, okay, maybe we should try different methods, right? Instead of just doing that endlessly. So we will try how vision models, these large models, language models, will help these vehicles make better decisions. So this is what I talk about: higher level of intelligence and a regular level of intelligence. So in this paper, eventually we worked. There's a system we developed eventually. So the model or the whatever it is, right? It's an autonomous vehicle. They will see the environment in front of you, and then they will understand the scene. They can detect, right, or do all the detection things we just talked about. But then they will understand the scene, and they will summarize the scene. Oh, there's a pedestrian, there's a sidewalk, there's a crosswalk, and there's even red light. There's a no turn on red sign here. And then they will retrieve. We developed there's a technology called RAG, Retrieval Augmented Generation. This is basically a database for large models, for language models. So we dump all the traffic rules and regulations in that RAG database system, and then we say, hey, depending on what you see, the vehicle state and the environmental state, and extract all the corresponding traffic rules that is relevant. And always we have to do some optimization work to make sure that the system is reliable. And then they will tell you, is it compliant with the traffic rules or not? Right? Is it safe or not? And again, compliance of traffic rules and safety doesn't always go along with each other, right? Because there's a big block in front of you, and it's a double yellow line. I have to, if I'm so fast, I have to cross that double yellow line. That's not compliant with traffic rules, but that's absolutely a safe decision, right? So it's just that it's not totally safety and compliance and not necessarily go together. But anyway, so this is the whole system, and it was very interesting work we did, and we integrate with the traditional planner, right? So basically, the system tells the automated vehicle that okay, is it compliant with traffic rules? And then it goes to objective function of trajectory planning. It's a very traditional planner. And the legality is that part, but also it has to be weighted average of safety, energy, smoothness, and so on. So we did that, and we put it on a vehicle. Obviously, this is a very interesting scenario. I think Waymo, many years ago, made a mistake. There's a video about Waymo. They made a mistake that, for example, there's a pedestrian still on the right lane, but this vehicle, 3 years ago, they must have fixed this, right? I trust them, they must have fixed this. The Waymo would make a lane change here and go across that using the left side lane, even though there's a pedestrian on the sidewalk on the right side lane. by nature, this is illegal, but it's safe, right? There's enough safe buffer here, you know. I changed my lane, right? I made sure it's safe, but by nature it's illegal. So we actually, in this example, we extracted that it's illegal. You cannot do that. So you have the only thing you have to do is slow down and wait for the pedestrians to bypass. So this is another experiment we did. You know, it's kind of also this is in the planner, right? Real time, we're looking at the scene detection. That's the first part we'll talk about. But then this high level intelligence extracting texts, extracting the scene, and match to the corresponding state, and then determine, right? Am I compliant or not? Last piece I want to mention is that we have, you know, some recent work we are exploring that even further this type of intelligence, because what you just see now is that, okay, I have a lot of language models to decide it's good or bad to do something, and eventually it wasn't directly related to my action. So what we try to do is is give these models a little more intelligence. I know I'm out of time a little bit. I can do this quickly. So we actually take this vision language models and further added action to it. Basically, these vision language models will output actions directly. Now, this is a little controversial. I know the industry loves it, but academia, at least for now, is kind of hesitant to do it. But we just went ahead, and because we did the earlier work, so we went ahead and did it. And you know, it's just good and bad things, right? One of the very important things I want to mention this quickly is that the reasoning part, even in the previous study, the reasoning part takes too much time. We love reasoning because this gives you a high level of intelligence, but the reasoning, like outputting all this text, think about you using, if you're not familiar with this, where you can think about it's just outputting this text reasoning. Oh, it is something in front of me, I have to slow down, I have to do this something. That type of reasoning takes a lot of time. So and there's a delay between actual reasoning, you're planning, and the control, right? Because the control, frankly, has to be like 10 hertz at least, right? So you have to be at that frequency. So there's two problems we actually solve in the two papers. One is this, we're using a kind of dual thinking mode. We train a model to be able to say like, oh, it's a simple scenario, right? I don't need to reason. Like I just output actions directly. But in some difficult scenarios like that, right? The picture on the left is pretty simple. The picture on the right is a place where you need some type of reasoning. And I'll skip this model performance. But the other problem we talk about is the reasoning and the control gap. So this is the somehow it's a little messed up here. But the idea is that thinking can take this long, but the control should happen here, all the time. So how you close this gap is a big problem. I think this is a very unique problem. We looked at literature, nobody actually addressed this. So we developed a model, right? This is my last few slides, that actually explicitly consider, because I know where the vehicles were when, I know all the metadata from all these systems, right? When they send out these messages, the lots of reasoning data, and I know where I am. I know exactly where I am, like when this reasoning data was generated. So I can learn that difference, right? And be able to control whatever vehicles and we actually tested this on this robots because it was too much work. Our student doesn't want to do it on the vehicle, so they actually tested it on this mobile robots. The idea is that I see something, I expect there's a control delay. No matter it's dynamic objects or it's a static objects, I expect there's control delay. So our results actually significantly reduce the collision rate. Because there's that type of anticipation embedded in our trained models. Last slides. This is something we want to do in the future. This is the recent video. When I saw this, I kind of downloaded it immediately. I hope Waymo doesn't hate me, but it's everywhere online, so you can see it. The problem is that these old vehicles, right, can't, they see each other, okay, let's back up. I want to back, you back. Oh no, you back, I back, then how about we, so they have no coordination, that's the idea. So there's many ways you can solve this problem, but definitely, for example, the so another distraction. There's a, the delay between the reasoning and the control, there's definitely a big gap. Now, by the way, I think at the end, the remote operator jumps in and solves this problem. I don't think the vehicle actually fixed, I guess, my guess, right? I don't think they figure it out by themselves. So this really has the implication of multiple things. We need, we need a couple of things. There's a delay between what they see, what they reason, and what they control, right? With that delay, that's what happens, right? You go back and together all the time. So if you really need to anticipate what others going to happen, and that's, again, it's a multi-agent system. So adding that reasoning, that high-level intelligence with this multi-agent system concept is critical. You can jointly train them, right, in a way that, like traditional when we do game theory, that's how we train multi-agents together. But again, it's a very nice case of using V2X communication. Share some sort of information. I don't even need to share that heavy V2X, like packaged information. Share some sort of information will definitely help you, right? I'll just end on this exam. Thank you so much for your attention.
Questions? I'm sure there are a lot of questions. Go ahead, Dr. Ali.
Hi, Samueli. Thank you for this great presentation, and also thank you for helping me with the papers at SRP and BRIS.
Oh, absolutely.
I really have two major, general questions on connected vehicles.
Yes.
Out of your work, how much you have, you reviewed the literature and all, how much of the papers, if you put a percentage on those who have been using simulation, purely just theoretical simulation assumptions, versus those who use experiments like you in the real world and have results between, or mixed results between simulation and real applications where things are verified and validated in the field.
Mm.
If you were to put a percentage, would that be 90% simulation, 10% experiment, or even less than that? And then if that is very low, if that's very low, then what do you think that percentage will switch to a much higher percentage with those experimentation? Where does it end, how soon will it climb? The experimental world.
Yeah, I think the CAV, right, let's just call it CAV, right? It's a field that has been popular for past 10 years, I think, at least 10 years. Most of the work has been in simulation, right? I would say, I think more than 90%, because every TRB we see a lot of papers.
Well,
I guess your community got a lot of papers too on that, even. I'm with you. I think a lot of the systems, the oversimplistic assumptions of pneumatic communication or vehicle behavior in those simulation has causing problems. We have been picturing too many advanced applications. Like platooning, right? I'm not criticizing platooning, but I think platooning, I worked on platooning in the past, by the way. I wrote public papers on that, but it's a very far away applications. It's very difficult to implement from a lot of practical perspective. In the 90s, Berkeley did a platooning experiment, but it seems that they didn't do, nothing happened after that. So I think we need more of this type of work, right? Not necessarily mine, the field work that shows what are the real constraints and what are possible applications. Otherwise, V2X as a field is hard to move forward. That's what I.
Then my second part is, what would the practitioners do with this? It's like, what is a major takeaway for somebody who's an engineer that works for FDOT or Caltrans? How can they make use of all this? What are major takeaways?
Yeah, one of the example I can give is this we call connected intersection or intersection safety systems. So the idea is, as I presented, is that you have sensors installed, and then you grab information and send out the messages, or even to the TIM message, to the traffic signs, warning signs. A lot of work we did in simulation for sure, but also field is testing, is understanding the combination of different sensors on a different environment, and developing algorithms to calibrate across different sensors. It's funny that I've worked with Caltrans quite a bit, California Department of Transportation. So and I think one of the reason one of our projects exists is that they came to me and say, there's so many LiDAR vendors come to me and say, oh, my system can help you detect everything, right? You know, but I don't know, are they good? Oh, is LiDAR the future? We have to use LiDAR now instead of just cameras? So I think there's a lot of questions like that in your head, especially from an infrastructure investment perspective. I think field experiments like this, and also simulation, right? Testing out different sensitivities will help them to make it, infrastructure decisions.
Thank you. I saw a hand here. Yes, Charlotte.
So, how will this system work in so V2X is definitely has much more advantage, but there is, so for example, there is a LiDAR on an intersection and the vehicle is moving, right? So when it crosses the intersection and that LiDAR is no more seeing, so a model that is trained on V2X perception, like where both the data feeds were coming, and now the vehicle has crossed that location, and now the intersection sensor the data is not what there is streaming no more. So in that scenario, will that model degrade in a drastic fashion that, okay, now since only there is one feed from the vehicles on LiDAR?
So we actually tested it. So the market penetration was the biggest problem in connected vehicles, V2X program. So because you share what you see, so really at a major intersection, you just only 3 to 4 vehicles. We actually have a diagram. The performance will plateau because you see all the vehicles you share with each other. So you only need 3 to 4 vehicles and infrastructure, 3 or 4 nodes, I would say, right? You will almost reach a pretty nice performance. So that's now obviously if you have less vehicles, yes, 1, 2, 3, 4, right? It's like this. So 2, 3 is kind of critical. If you have two as compared to 3, I think that performance is still different, especially at major intersections.
So I had a related question. Earlier you mentioned you talked to OEMs, right? And first part of your presentation was about the cooperative perception.
Yes.
For example, right now all these models are being trained from the OEM perspective, Tesla, Waymo, as a single vehicle, right?
Yeah.
They are not going cooperative.
No.
So if we are approaching in that direction, and we are almost there, FSD is being released, with some supervision. So is there a real need for cooperative perception? Will there be in the future?
Yeah, I think, first of all, industry, especially what we call ADS developers, which is like Waymo or Tesla, they obviously they will not admit they need infrastructure data, right? Because their mission is to give you a product that's safe by itself. So they will never say, I need your data. On the other hand, so even their models, I mean, the kind of, for example, the traffic rules regulation work I did, that's actually from an individual vehicle perspective. So you can still build some capabilities, extra capabilities from infrastructure, share those type of data, right? Instead of the heavy V2X data, right? The standardized basic safety messages, the sensor data sharing messages. So those are the heavy approach, right? I call heavy V2X approach or light V2X approach. Now, again, I think V2X is a mission. So we have to, there's a lot of advantages of these approaches, like coder perception. It's a mission to me, I want to find different scenarios, different message types that will actually inform OEMs. Now, on one of the projects I will quickly mention, we've been interviewing about 10 different OEMs and ADS developers. My question is, I know some of those companies, when I went into the meeting, I know these guys will all say, this is useless, I'm not gonna use it. But luckily, right, the guy I was worried a lot about, when I went to the meeting, he's like, I'm not sure. But then at the end of the meeting, I told him, I'm not talking about, I'm your sensor, right? I'm talking about providing information to you when you need it. Now you tell me different scenarios that you need those information. So he actually gave me multiple scenarios that Waymo has challenges, or other companies. These companies have challenges, not just Waymo, right, but the other ADS developers have challenges by themselves, right? So I think color perception has a role here. Now, obviously, another question we talked about this morning is the data validity, right? So as an infrastructure, data provider, researcher, my first job is to making sure my data is valid, is accurate. And then they can